Tyler. We're going to spend, I guess, 25 to 30 minutes today talking about how you can turn your database into real-time events. So why would we want to do that? There's a lot of use cases for that. Live updates. Has anyone used Linear as a task tracking? Yeah, it's awesome, right? You're like editing something, updating a task, and like everybody else on your team just sees that in real time. Feels super snappy because it's all like broadcasting these changes to every other user of the app. Collaboration. Everybody's used like Notion, Google Docs, maybe like some whiteboarding tools. You see this like real time syncing even like down to the mouse cursor level. Audit logs for a lot of industries like healthcare or insurance or finance. You need to keep a track of changes that have happened on your system, be able to kind of play back through, see when something changed. This is my favorite one, side effect workflows. How often are you building something where you need to, maybe you are in a create user flow and you want to send them a welcome email, or you need to create their user record in Stripe or customer record. Having to sync to that external system, like push that change out, is what I would call like a side effect. And then push notifications, we all get those on our phones. Sometimes they're marketing, sometimes they're helpful. Sometimes we get to filter them out a little bit. And then synchronization, when you have a lot of businesses are running on many systems, right? So keeping all those systems in sync with all the changes going into your primary system is a challenge. So these are all reasons why we'd want to adopt something that's more event-driven, something that's more right at once, push it to all the other systems, and everything's going to catch up eventually. So a quick story. Yesterday I came down from up from North Carolina. I took the train because I thought it'd be a lot of fun, do some sightseeing. That was supposed to be like 9 hours. It turned into about 12. So you can see kind of the path I took there. But along the way, I got these really nice notifications from Amtrak. So you can see on my phone on the left, emails on the right. I also got text messages. They were keeping me up to date of, hey, we had another delay. This is when we're projecting you to arrive now. I wasn't necessarily happy about it, but I was happy that I was told what was happening. And the coolest part is these all hit my device like all about the same time, right? Everything was in sync. I clicked the link. It shows the right schedule. There was no inconsistency with any of the messaging. As a counter example, I booked a flight home for tomorrow because I didn't want to risk the train again. And in doing so, I hadn't flown American in a while, needed to put in my TSA pre-check number. And when I did that, they sent me the email that, hey, something changed on your profile. Maybe it was your email preferences, maybe it wasn't. In my case, I didn't change my email. But it might take 10 days to update that. And I'm looking at this and thinking, why the heck does it take 10 days to, like, if I actually changed my email, that would be really annoying to get, like, not get emails to my new email account for 10 days. And immediately I'm thinking, why would they do that? Well, they've got thousands and thousands of users. And if they need to sync their database to some other like mailing list system, they can't do that minutely, hourly, even daily. So maybe that's a reason why it's 10 days, maybe not. But yeah, so these are like just completely different experiences, right? And why we might want to drive things to more event-driven. So a bit about me. I'm Tyler Benfield. I'm a staff software engineer at Prisma. Prisma builds a lot of database tooling, especially for the Node ecosystem. We'll get into more of that later if I've got some time. You can find me on Twitter, X at RTBenfield, and also on Blue Sky at rtbenfield.dev. Quick plan, we're going to talk about event-driven architectures. We're going to look at how Postgres change data capture works as one of those. We're going to maybe take a look at some code really quick if we have time, look at some off-the-shelf options for adopting event-driven architectures this way, and then we'll wrap up. Okay, event-driven architectures. So I've got a definition of what I would call the gold standard here. These are the things that I'm looking for anytime I'm building something event-driven. It needs to be instant, like for users, imperceivable latency. That means no polling, no 1 second like hitting the database all the time. And that then means we need an always-on active connection that is pushing changes to us. It needs to be consistent, like I mentioned with the Amtrak example. If I click on a notification, I want to see the right data there. Everything needs to match, and the events need to always trigger anytime the changes happen. In most cases, the events need to be ordered for all the recipients. Imagine if you are pushing changes in like Notion and you send them out of order to the page, well, you might get the wrong data pop in because somebody is like live editing and the wrong edit comes in at the wrong time. And then recovery, if a client disconnects and needs to be able to reconnect, pick up where it left off, replay any messages, and handle some amount of downtime. So that's what we're going to be looking for. A common solution for that is dual write. This is where you would write to both your database and your message queue at the same time. And then your application is reading from the database and subscribing to changes. Might look something like this. You've got a request handler that's using, like concurrently saving data to the database, pushing message to the queue. Problem with that is what happens if the database write succeeds but the message queue fails? Well, now you've got data in the database that is up to date and accurate, but maybe you didn't send that email, or you didn't run that sync to Stripe. And then on the flip side, you could have the database write fail and the message queue sends out, which is a worst case. I just sent a notification to somebody that maybe their order was processed, but it wasn't. So for that solution, we do get it instant, but we're not consistent. It's not going to be represented all the time on both sides. They can be ordered if we're using a good message queue. And recovery, if we can't guarantee consistency, we can't guarantee recovery. So then there's a write first, read eventually. We write the message to the message queue first. Some processor picks that up and then updates the database, and then the app is reading from the database and subscribing to the message queue. Seems like we solved the problem, right? Except what happens if, a quick example of that one, skip through that. Yeah, what happens if the queue processor fails? So we sent the message, we sent the notification, but then we didn't update the database. Now we can do retries here. We can eventually get the database correct, but there's going to be some lag time. So now that consistency and real time, that kind of goes away. So we mostly get it instant in the terms of the message queue did get the notification out to the user, but we can't guarantee consistency at that point in time. It could be very delayed. But it is ordered, and now we have recovery because we can retry those messages, retry updating the database. And we get to the outbox pattern. So we can use a transaction to write data to our database into both the actual table and into an outbox table, which is kind of like a log of the events that we want to push to some other system. This works really nicely because we can put it in the same transaction. So we know it's going to commit to both of those at the same time. There's no chance of one happening without the other. But the downside of this is our application now has to pull that outbox table to look for the events there, and then it can process them that way. So a little example of that, you can wrap it in a transaction, and then you store the data and add it to the outbox. We know it's going to work consistently every time because they're in that transaction. But what happens if we forget to write to the outbox? So maybe we did a manual bulk import of some data, and we inserted into, say, our users table, but we forgot to write to the outbox table. Well, now we've got to go try to clean up our mess that we made because we were doing something out of band. So it's not instant. We had to do polling. It can be consistent if you remember to actually write it to the outbox. I don't trust myself to do that, so I wouldn't necessarily consider it consistent. And it's ordered because we can make sure that those events in the outbox are ordered by some incrementing value. And it is recoverable because we can at any time ask the outbox for more data. We don't have to delete data from it until we've actually processed it. So then the magic solution, change data capture. This is what I want to talk about today. The application just writes to the database. Your editor, your IDE, whatever, you're writing directly to the database. You don't think about any of the event-driven things, but you have an application that is consuming from the database and reading those changes. The database is actually telling the application that the data has changed, and then you react to it. And in reality, that's a little bit more complicated. You can't just have your application connect directly to your data. Well, you can, but there's some challenges to having your application to connect directly to your database this way. So we often set up what I would call a CDC service that is watching the database and getting those changes, and then pushing them to that message queue that we had in our earlier architectures, and then your application's reacting to that. That message queue gives you that really good durability and delivery of those events, but you have this service that's reading it from the database. So now when you're updating data, you only write to the database, and it broadcasts it through to any consumers through the CDC service. That gives us instant. The changes are immediately pushed from the database to our apps. It's consistent because we can know that if the data went into the database, it's going to go through this message queue flow. It's ordered because the database has preserved the ordering when we do this, and it's recoverable. If that CDC service goes down, the database will actually hold on to the changes until it comes back up, catches up where it left off, and pushes them through the message queue. Everything processes. So there's a lot of flavors of CDC for various databases. In Postgres, you have logical replication. We'll take a look at that one today. In MySQL, MariaDB, you have the bin log. In MongoDB, you have a concept called change streams. CockroachDB actually has this thing called change feeds where you can do webhooks, Kafka, PubSub, probably some other options. SQL Server has SQL Server agent jobs. And in SQLite, they have this data change notification callback that you can hook into if you're working at a lower level of SQLite. It'll tell you anytime into your app when you change data from elsewhere in the app. So let's dive into Postgres CDC a bit deeper. There's some terms here that are going to come up a lot, so I'll try to gloss over these really quick. We have the write-ahead log. This is how the database tracks changes that have happened before it commits them into the actual data files of Postgres. It's literally a log of every change that's happened on the database. It can write to it really quickly, and it can use that to replicate to other database instances. And then we have a log sequence number, which just represents a position in that write-ahead log. So it's like split in half. One half is going to be which write-ahead log file it refers to. The other half is literally a byte offset in that file of this very particular event. A publication is a definition of tables that we make available for logical replication. We'll see an example of that one. A replication slot is a particular instance of another replica or an application that's going to be consuming these events. We'll also see an example of that. And I want to distinguish between logical replication and physical replication. This is, again, like Postgres specific, but logical replication is the idea of replicating the changes by sort of a delta. Like you're telling another server, this is a record that changed and here's what changed about it. I don't care how that's represented on disk. I only want to tell you that this change happened. The cool thing is that lets you replicate in Postgres across different versions, for example. And then physical replication is copying blocks of memory. So it's the primary telling the standby, hey, this block of data changed and I want you to just drop it in place. You don't have to look at it. We're not going to talk about physical replication. We're going to talk about logical replication. All right, so the write-ahead log. Like I said, that's a log that Postgres tracks of all the changes that have happened on the database. It's used to recover after Postgres crashes. It's used to replicate to other standby servers, like if you want to run a high availability Postgres cluster. And it is server level, not database level. That nuance really just comes in if you're dealing with the protocol stuff we're going to be looking at later. If you want to learn a lot more about the write-ahead log, Crunchy Data has a really good blog post on that. We don't need to get to that level today. So logical replication, we talked a bit about this. It leverages that wall to stream changes to other servers. The events get encoded in a format that we can choose that the standby server is going to recognize. The standby server receives the events through an active connection, so it's pushing these changes to the standby. And the primary is going to keep the changes until that standby says, I've received them, I'm caught up. And that's really important for the workflows that we're trying to get with that consistency and recovery. Replication slots. It tracks the position of the wall, so the primary actually knows that there is 1, 2, 3 replicas that it needs to stream to and where each of them are at. And that's how it knows I can't delete this older wall data until this replica has caught up. Only one application can be connected to a particular replication slot at a time, because if there's 2 of them, then they're both reading changes. One of them acknowledges the event, the other one doesn't. It just gets things out of sync. So it's restricted to 1 at a time. And Postgres limits the number of replication slots you can have on a particular server because it does add some more load. And we talked about the Postgres retaining the wall data. So becoming an imposter. What if we told the database that our application was actually a replica? The database is going to start sending us all the changes in this encoded format as they happen on the database. And then our application just needs to know how to decode those messages and then tell the database server, I got it, we're good. I'm caught up. So there's a few commands we'll use. We'll see these in the code, but we'll create a publication. Publication, again, is that definition of tables you want to replicate. We'll do it for all tables, but you can also narrow it down to a particular schema, a particular set of tables. There's a few options there. We'll use PG create logical replication slot. That's a lot to say. To create the replication slot, give it a name, and we tell it what encoding plugin we want to use. So Postgres ships with this PG output one, which is a binary protocol. That's what we're going to look at. There's also a test decoding that you can see a text version. A lot of people use this wall to JSON one that ships in a lot of distributions of Postgres, but it does it in JSON format. You can even write your own. A good maintenance method is PG replication slots. You can see the position of a particular replication slot. How far is it off of the current position of the primary server? Is there an active process connected to it reading it? It's really good for monitoring. The start replication slot command is what we'll use to actually connect in and start streaming those changes. So that's just a SQL command that this app is going to run. We tell it what slot we want to connect to. We tell it that we want to start from a particular LSN position. And then we give it options that we want to pass into the plugin that we're using for decoding. We can also use PG logical slot peak changes to ask the database, like, hey, what's in that replication slot? I don't want to stream it. I just want to poll against it and see what's in there. One more utility is PG replication slot advanced. This is really helpful if you ever get a replication slot stuck. You can manually tell it like, hey, just proceed forward. That's important to keep the database healthy. If you have a replication slot that's kind of like not active anymore, Postgres will just keep this backlog building up because it thinks the replica needs to catch up. You can just tell it, skip all that, let it be deleted. And then we'll drop the replication slot later and drop the publication. Okay, so that was a lot of stuff. Let's take a look at some code real quick. This QR code here will jump to a repo that we literally just open sourced today. So let us know if you have any feedback on it. But we're going to take a look at how our product Prisma Pulse, we open sourced the CDC aspect of that. And that's what I want to show off today, because this is really cool. So this repo, and I'm going to wing a lot of this. This is the least scripted part of my talk. So I've got a Docker Compose here that just starts a basic Postgres 16 server. I haven't updated 17 yet. On a port number, I give it this argument of I want the wall level to be logical. So that tells Postgres, like, hey, you need to start storing these changes at a logical level instead of a physical level. Adds a little bit extra weight to the write-ahead log, but it's worth it. And then I've got some basic like local stuff. You can steal the password here. It's just my local machine. So I'm going to Docker Compose up that. That starts the database up. Everything's good. I've got a simple script over here to demo how this works. If I can, there we go. This is all setup stuff. It does that create publication we were mentioning, the create logical replication slot, so we get everything set up here. But the cool part is down here in this replication stream. So this open source package we just published, it has this logical replication stream utility. In fact, this is all JavaScript, TypeScript. Hope that's familiar enough for everyone. This is built on top of NodePG, and it connects to the database using this like config that we give it here. And then it connects to the replication or the publication name and the replication slot that we want to use. That then opens up a stream that we can start reading data from, but that data is going to be in a very binary format. It hasn't been decoded yet. So we pipe it through this PG output decoder. PG output was that plugin that we told it earlier that we wanted it to encode in. And then from there, we can just literally like for a wait loop over the messages that come from this stream. So let's see what that looks like. Cool, so I started up and I immediately get some messages. And we see they're like keep alive messages. That's the primary is telling us, hey, standby, are you still there? Are you still listening? And then we have to like acknowledge those back to say, yeah, we got it, we're active, don't give up on us yet. Let's go over here to Azure Data Studio. And I think I've already got this table in here. Yeah, cool, already exists. And let me collapse this so you can see it a bit better. So if I do an insert over here, you can see on the left, like instantly, I'm getting changes. And if we kind of filter through this a little bit, you can see that one of these is actually like a wall data type. It has this LSM position to it. That's like that incrementing value that represents its position. And then inside of the message, we can see what type it was. So in this case, it's a commit. It has like a timestamp. But if we go up a little bit higher, there's an insert. And it has the relation data, so which table was it affecting, what columns are in that table, and we get the new data that went in. So if I add literally anything over here, run it again, I should see, yeah, there's 1, 2, 3. So instantly, real time, streaming the data. There's no magic here. This is literally just feeding off of the database as I insert it. This is like mind-blowing to me because it means like somebody goes and does a manual script to import data, and all of my workflows run. I don't have to remember to rerun a bunch of background stuff. And this works for deletes, updates, all of that. Okay, so that's cool. That's a basic example. Let's do something a little more fun then. I'm going to kill that one. And I've got this chat example. It's the dumbest chat you'll ever see. And I'm going to try to do this on ngrok 5173. I don't know how well this will work. Okay, cool. So if y'all want to have some fun, I'll do a QR code here. So if you want to scan that, you can open it up and start sending some messages through. And hopefully this all works, live demo stuff. And I didn't actually put any of the text that you put in here because I don't trust any of y'all for a live demo to show text on the screen. So instead, I'm pulling quotes from National Treasure. So anytime you send a message, we actually capture it, but it's just going to replace whatever you put in with this. So you can see how fast this is too. It is like, I don't know if you're noticing when you hit the button, it is very fast. Now granted, this is running on my local machine. This is also over conference Wi-Fi, so pretty cool. I don't know, that to me is really interesting. So you can build like chat apps with this. You could build side effect workflows, all that sort of stuff. And I'm happy to, we don't really have time today, but I'm happy to dive into the code here and show like how we actually decode this. Once you learn it, it's pretty straightforward how you get this like chunk of byte data back from Postgres. And it's very well defined how to turn that into like usable data and then send an acknowledgement back to Postgres that you got it. All right, I'm going to kill this now. So, oh, and we can see the logs here of all the messages coming through. OK, back to the talk. So where do we go from there? What can we do with this? You probably don't want to build all that yourself because there's a lot of edge cases you'll have to cover. Like what if your app goes down? It'll cause Postgres to start building up a big backlog of things. You want to make sure you like monitor this app well. How do you deliver those events to a consuming application? Maybe you want to stand up a message queue. For a lot of reasons, you probably don't want to write the level that we wrote to build Pulse. So there's a few off-the-shelf solutions. I'm going to talk about two of them. One is Debezium. It's an open source, self-hosted solution for capturing these database changes. It supports a bunch of databases, Postgres, MySQL, Mongo, all the popular ones you'd want to use. You pair it with a message queue or something like Kafka, RabbitMQ, anything you'd want to use to get that durability and distribute the events out to all the consumers. And it's completely free to host this yourself, totally open source. It's fun to try out. Prisma Pulse is our solution to this. It's fully managed, totally hosted. You don't have to really run anything yourself. It only supports Postgres right now, but we have plans to extend it into more. We build in the durability and delivery and long-term event storage. And it also integrates with our Prisma ORM really well to give you like type saved in your JavaScript events. It can be used with any node application, though. You don't have to be using Prisma already as an ORM. You can still adopt Pulse. And it is one of our paid products in Prisma because we're hosting infrastructure to power this. But that open source stuff we just looked at is the like backbone of how Pulse does its CDC stuff. And then we add in all the infrastructure for storing the changes, relaying them to consumers, all that fun stuff. So let's talk about Debezium a bit because this is really cool architecture. You can deploy it into a Kafka with Kafka Connect. You point it at a database, and it'll start consuming the events and then pushing them into Kafka topics. And then your applications can start using that to push it into things like Elastic, push it into your data warehouse, push it to your consuming apps. So if you're already running a Kafka cluster, this is a really good way to get started with change data capture. Debezium Server is more of a standalone solution. You can run it as a process or as a Docker container. You start it up, also just connect it to your database, and then you tell it where you want to send the events to. So if you wanted to run this in like a container runtime, this is the way to go. And then you configure like where you want the events to sort of relay to and then fan out from there. Then that puts the responsibility of like durability, recovery, forwarding the events to consumers all on whatever delivery mechanism you use. Oh, and one important thing is make sure your destination can handle the throughput that you're processing too, because databases can produce a lot of change events, especially a busy database. You want to make sure that like this whole funnel is able to keep up. And that was one of the things we tested Debezium when we were building Pulse. We really liked it, but we found that like the network hops between the different pieces of our event funnel were actually causing a bottleneck on the events, and that's why we ended up writing our own. And then there's Debezium Engine. So if you're a Java developer, you can go grab this as a jar, bring it into your app, and then your app can actually do the work of Debezium. I'll also caution you, though, that, again, make sure your workflow can handle the throughput of your database. Otherwise, you're going to get a backlog. It's much, much better to pipe it to some kind of message queue delivery system that can take that load off of the initial app that has to consume the data. And then we have Prisma Pulse. That, like I said, is a hosted all-in-one solution. It connects to your database, configures itself, and then immediately starts capturing the changes that are occurring. And then all the changes are recorded to our own custom storage engine that we wrote for this. It's optimized for like a high throughput write, and then offloads in an archive fashion to like a tier 2 that's blob storage, so it's incredibly cheap to keep these long term. Kind of replaces that like Kafka layer in Debezium. That allows us to offer like long-term retention at really low cost. And applications can subscribe to the changes with delivery guarantees and resumability. We give like a front-end SDK or front-end, but like a end-user SDK to consume these changes into your backend and then do meaningful things with them. Now I talked about the two-tier storage. That's really where we extend from the open source stuff into the hosted offering, is adding that storage layer. And this is what it looks like to use Pulse. You literally say like prisma.notification, that's like your table name. You want to stream it. You can tell it, I only want create events where deliver is false. We do all the filtering on the back end so we don't overload your app with a bunch of events you didn't care about. And then just a for wait loop. Just like we saw in the open source example too, this one's just a step later where it can apply filtering and transformations, that sort of thing. And this is all type safe based off the types that the Prisma ORM gives you. So recap real quick, the gold standard for event delivery. Instant, no latency, always active connection, consistent. When we write the data to the database, we get the events every time without missing them. They're ordered, so we know that the changes that we get to whatever our consumer is are going to be in the right order, and we can trust that to build things like Notion much easier. And recovery, if it goes down for a bit and it comes back online, it should be able to catch up, pick up where it left off. And yeah, thanks for being awesome. That's all I had.